Welcome to this explainer. Designing an elegant software architecture is really just half the battle. Think of this as your masterclass in the post-design lifecycle. Because your real test as a lead architect, that begins the second the blueprints are drawn and your code actually hits the real world. So, how do you keep it from turning into a chaotic mess over time? Let's dive right in. Okay, here's our syllabus for today. We're mapping out 5 actionable skills you need to master to keep your system from collapsing. Building it right, testing the architecture, reconstructing lost systems, spotting rule violations, and finally, evaluating the final design. Let's get to it. Moving right into Module 1, building it right. Your primary assignment here is simple, but absolutely crucial, and that's preventing what we call architecture erosion. Let's open up your Architect's Toolkit. To make sure your developers actually build what you designed, you need mechanisms to enforce that alignment. This ranges from simply embedding your design directly into the code using comments and conventions, all the way to deploying rigid frameworks like Ruby on Rails or AutoSAR. You're also going to heavily rely on code templates for repeating protocols and automated tools to enforce your rules during the build process itself. And honestly, here's why templates are literally your best friend. Imagine engineering a complex, hot standby failover. It's tough, right? Well, instead of letting everyone reinvent the wheel, you have your top, highly skilled engineers solve that complicated problem exactly once inside a code template. From there, your less experienced developers just plug their application-specific code right into the designated slots. It guarantees architectural consistency across the board. All right, let's advance to Module 2, testing the architecture. This is where we actively drive the test harness to check for functional correctness and do some fault injection. Now, I want you to imagine a tiny error slips through your testing phase. It causes a mere 2% performance degradation on a single server. You might think, hey, in isolation, that looks like normal variation, right? No big deal. Well, actually, wrong. That is the danger of network effects. When you take that tiny 2% drop and deploy it at scale across thousands of servers, it turns into a catastrophic failure. A minor routing delay in a unit test multiplies exponentially in the real world. The big lesson here? You have to design self-aware systems that monitor themselves to catch these cascading network effects before they take you offline. On to Module 3, reconstructing lost architectures. What happens when you're hired to rescue a massive legacy system, but the original developers are long gone and the blueprints are completely lost? It's basically the architect's ultimate nightmare. Zero documentation, and every single change risks breaking the whole system. But don't panic. You actually have a specific forensic technique for solving this exact mystery. It's called architecture reconstruction. You're essentially acting as a software detective here, reverse engineering the as-built architecture directly from the surviving artifacts. You'll use tools to scour the source code, look at execution traces, dig into build scripts, all to uncover the hidden structure that actually exists. Here is your step-by-step reconstruction playbook. Step 1, raw view extraction. You use parsers to pull raw data straight from the code. Step 2, database construction. Standardize that massive data dump into something readable. Step 3, view fusion. Layer the data to collapse all that white noise into distinct structures. And finally, architecture analysis. Test those fused views as hypotheses to see if they reflect reality. Now, to get an accurate picture during extraction, you absolutely must understand the critical difference between static and dynamic information. Static analysis using AST analyzers just reads the source code. But here's the thing. Static code lies. Thanks to late binding, plugins, and polymorphism, the true topology of a system isn't determined until runtime. You've got to fuse that static data with dynamic runtime information captured by profilers. Otherwise, the real truth stays totally hidden. Section 4. Spotting rule violations. Once you've rebuilt those architectural views, it's time to grade the system and catch exactly where developers broke the rules. With your hypotheses built, you apply your strict architectural constraints. Say a data layer is secretly bypassing protocols to access a forbidden testing tool, maybe something like JUnit in production. Well, automated tools like SonarJ will automatically flag those illegal cross-layer dependencies. You instantly catch the exact point of erosion. Let's look at a real-world case, the Dukes Bank sample application. The documented architecture strictly forbade direct database writes. To a static parser, everything looked totally perfect. But when architects used AspectJ to instrument the runtime code, the dynamic analysis caught the system secretly writing directly to the database. It was a massive, invisible violation that was impossible to find just by reading the code. That is the unmatched power of dynamic reconstruction. Finally, Module 5, Evaluating the Final Design. Let's talk about how to test your completed architecture before it accidentally ruins a business. Listen, not every evaluation requires a massive audit. You can actually run a peer review in half a day just by following these 4 steps. Determine your quality attribute scenarios, like a sudden traffic spike. Then present the design, walk through those hypothetical scenarios as a team, and explicitly decide whether to fix the exposed vulnerabilities or just accept the risk. But when stakes are incredibly high and millions of dollars are on the line, a half-day review just won't cut it. That's when you bring in an external ATAM team. The architecture trade-off analysis method is comprehensive. It requires 20 to 30 person days of effort from objective outsiders who aren't afraid to tell you that your baby is ugly. They rigorously interrogate the system to make sure the technical design maps directly to the actual business goals. The ATAM process generates some absolutely vital artifacts. It maps out a utility tree of quality attributes, groups risks into themes, and most importantly, it identifies sensitivity and trade-off points. A sensitivity point is where a single architectural decision drastically impacts a quality attribute. For example, how a heartbeat frequency dictates both your fault detection speed and your network drag. Finding these points before coding begins is invaluable. Now, if you don't have 30 days to spare, here's a blueprint for a lightweight architectural evaluation you can run internally in just 4 to 6 hours. You spend a fraction of an hour on business drivers and module overviews, and then dedicate the bulk of the session, about 3 hours, to analyzing architectural approaches against your mapped scenarios. It's a fantastic, low-ceremony evaluation that can save you from catastrophic flaws down the road. We've covered a ton of ground in this masterclass, from preventing code erosion to forensically reconstructing lost systems. So as you head back to your own code bases, I want you to ask yourself a question. If we pulled out the extraction tools and reconstructed your current project today, would it reveal a masterclass in design or a tangled web of spaghetti toad? Is your architecture surviving the real world or quietly eroding? Thanks for joining me for this explainer, and I'll catch you in the next one.